and I will do a indirect jump back to wherever I came from and so on, is a process of invocation. That's the specific process of apply in the context of a certain computational model that we implement. But apply by itself is a function which takes a function and applies and a value and applies that function onto that value. So that's these are just becomes convenient to build up further thing. Yeah. Here, Akshat, here the worked out example in terms of some other. So twice is similar to apply, but all that it does, it applies the function twice. So you f of x. That's, we have already explained it. Now, naturally, if you apply it twice, it has to be that the codomain and the domain must be the same set, because once if x belongs to set A and f of x belongs to set B, then you will not be able to apply f a second time. So it has to be both on the same set A. So twice takes a function f, which is from A to a value in x, value a x in A. I'm sorry. So it takes a function f, which is A to a, takes a value x, which is in A, does the application twice and gives you a value A. So here is an invocation of a use of this application twice, square, 3. So 2 parameters, square and 3. So if you write in longhand, this is what you get. So first you have to replace square for f. So if you do that, you get this, this lambda f is gone, you get square here, square here. So square x goes up to this, and you're left with the second parameter, which will replace x. So it comes to this lambda expression. Now square 3 is 9. So you come to square 9, it's 81. So in the same way, you can actually compute twice lambda in this in the longhand. So that's a twice function, twice lambda expression. Now similarly, you can do a thrice, 1, 2, 3. Actually, as we will see, you can create another meta applicator where you can say that this will apply the function n number of times. So I can have a lambda n here and make sure that it applies f n number of times. But certainly, if you have to do that, you need the concept of this kind of a loop or recursion. So it will come a little later. So far, it only fixed number of applications that we have. So if you do thrice and apply it on square 3, you will again go through that. But this is the result that we'll get. This was applied twice, gets you 81, and then you similarly add we'll get 8. Next, the function composition. So once you have seen apply, where the function applies is applied, and then again that function is used on top of it. Here we are generalizing that as a composition, which we call as comp. Again, remember that this is not the part of lambda calculus. This part is. So you have two functions, g and f now, and a parameter x, and comp gf first applies f onto x, and on the result it applies g. So having known the function composition in mathematics, as we have talked about earlier today, this is basically comp gf is basically g composition f. So what is the type of this comp? What is this lambda expression actually doing? So it applies f onto x. So let's say f is of type A to B and g is of type B to C. Then the type of g composition f is A to C, because it is taking a type of value x, which is of A, applies f onto it, gets a value which is of type B, applies g on that value, so it gets a result which is C. So g composition f is A to C. And the whole type of this lambda expression is it takes the first function g, which is b to c, a second function f, which is a to b, and then it applies to get a function a to c. So g and f, b to c and a to b, these two functions are taken, and in return comp gf gives you a new function which is a to c. Right? So that is a composition. Now naturally, as you can see, composition is a generalization of twice thrice. So twice f is nothing but comp ff. Twice thrice f is comp f of comp ff, or comp of comp ff and f, because applying the same function, the associativity really should not matter. Right? So this is another example of a lambda expression. So we have seen identity, we have seen successor, and we have seen apply, twice, thrice, composition, all of this. We have seen constants. Now we will see something which is very, very interesting, which will actually let us work towards a Boolean algebra. This function, forget about the true name first. First, call it by the name FST, which stands for first. What is this lambda expression? Lambda x dot lambda y dot x. So it takes two parameters. Okay. So let's take two parameters here. Lambda x dot lambda y dot x. Two parameters m and n. So m replaces x. So I do the first part of this application. M replaces x in this expression. So this becomes m. So it becomes lambda y dot m n. Now there is no instance of y in this expression m. Right? So like we saw in the case of constant functions, this, no matter what is n, this will always evaluate to m, because there is nothing to replace in m. So whatever I put as n, I'll get m. So this is, if I look at this lambda expression and I've tried to put it on two values m and n, and I get the first value m. Two lambda expressions m and n, and I get the first value m. So I call it the first selector function. So I say that if I have a pair of lambda expressions m and n, this lambda expression picks up the first one of the pair. Very interesting, right? It's kind of making a choice function, selector function in terms of lambda expression. So first, now rest of it is this types and all are easy. So first has a type A to B to A. So this is the first selector, and for now, just let us put that first selector function can also be given another name, true. We'll see why. Okay, so we have got the first of the two first component of a pair. So naturally there has to be a similar function which gets the second component of the pair. So earlier it was lambda x dot lambda y dot x. Now I have lambda x dot lambda y dot y, okay, which is the second selector function. Let's see why. Apply it on a pair mn. M replaces x in lambda y dot y. There is no x here. So replacing x by m has no result. So it is lambda y dot y of n. This is an identity function. Lambda y dot y is the ID function. So it's ID n n. So whatever is n, you replace that, you get n. So you can see that this lambda expression is like the previous one. This lambda expression also interestingly picks up a component, but it picks up the second component. So first selector function picks up the first component, second selector function picks up the second component. And let us choose to call it false. Right. Now the fun begins. I want to define a if lambda expression. Think about if, what sense does it come to our mind? If has a condition, a true part and a false part. So it says that if the condition is true, Boolean condition is true, then the true part will happen. If the Boolean condition is false, the false part will happen. So in terms of lambda expression, what you say is if takes three parameters. One is a Boolean argument, B. One is the true part expression, lambda expression, and one is the false part, lambda expression. Somebody's microphone has got unmuted. Please mute. Please mute. Then the expression is BTF. Right. So we say this behaves like if. How? Let us say that I apply this on this triplet. There are three variables, so I need a triplet. The first is true, then TF. Now, what is true? What is true is the first selector, right? So this lambda expression. This lambda expression TF is what I'm instantiating this on, applying if on. If this is true, then what it does from the pair, it picks up the first one, right? So it picks up T. This is the first selector. True is the first selector, so it picks up T. What if I put this on false, TF? This is the second selector, so it puts it F, right? So you can see that if this lambda expression behaves like if, where if B is true, that is if B is the first selector lambda expression, then it picks up T, the true expression, whatever that true expression is. But if B is false, that is the second selector function, second selector lambda expression, then it picks up F, which is the false expression, whatever that expression is. Now, naturally, if B is something other than true or false, if you give some other lambda expression other than the first selector or the second selector, then the result of if is undefined. Then you do not know what it means, right? So it's always possible, as I said, that you can have a lot of nonsense lambda expressions. Okay. Sorry. Now let's see. Now let's build up Boolean gates. And is this expression. Lambda B dot lambda B dashed if B dashed false. So what is AND? AND is, let's think about the normal Boolean logic. It's true if both variables are true and it's false otherwise, right? So let's say, how does that work? Let's say suppose B is true. When I instantiate this with B and B primed, if B is true, then here I get if true. So what I'll get, if true will give me the first component, which is B primed. So if B is true, the value of this expression is B primed, which is the AND function. Rather, the current version of the AND function. Because if B is true, then the AND is true only if B primed is true. Otherwise, it is false. So if I'm basically carrying on B, saying that if it is true, then the value is B primed. Okay. Now what happens is if B is false? If B is false, I have B false here. There's a second selector, so it picks up the second false. If B is false, the value of B prime does not matter. it will be false, right? So that's the, so this expression is nothing but the and the very interesting thing to note here, observe here is that when we build a Boolean algebra, we think about two constants, true and false. We say it is true and it is false. Now, what is true and what is false is actually immaterial till you define the logic based on them. So you can visualize them as 0, 1. Think of AND as, ANDing multiplication, or as inclusive addition, and so on. You can think of this as two abstract constant as true and false. You can think of it in any possible different way. For example, C thinks of true false as you know, is anything which is not 0 is true and anything which is 0 is false. So in a similar manner, here we have defined the primitives of a Boolean algebra based on lambda expression, where true is the first selected expression. In lambda calculus, everything is an expression. So every value is an expression. So this expression is my truth value. And this expression is my false value. So these are the two primitives of the Boolean algebra that we have got defined. And then we have defined a lambda expression for condition checking, which is now giving me the well-known gates that I have. Let us look at the OR gate, inclusive OR gate. Lambda b dot lambda b prime, naturally this will be same. If b true, b prime. So I will do currying again. Let's say if b is false. What is the value of OR? If b is false, then the value of OR is b primed. Because either one of them must be true. So if b is false, then it has to be b primed. So if b is false here, it picks up the second component. So it is b primed. If b is true, then the currying gives you that it is true. If b is true, then it is the first component which is true. So this behaves like an OR gate, OR function. So that's how, you have OR and AND. So all that you need is NOT, which is simply flipping. So if b is true, you need the first component, so you put it as false. If b is false, you get the second component, so you put it as true. So it simply flips. So you can see that you have, in terms of lambda expression, been able to define the well-known AND or NOT operations. And we know this triplet kind of gives you the universal logic. You could compose on NOT and 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 get a universal get NAND, or and NOT and get universal get NOR, and so on. And once you have AND or NOT, naturally it means that any expression in Boolean algebra can be written in terms of lambda expression. So lambda expression is actually as powerful as Boolean algebra. It's actually more powerful than that, but this is the way to show. So just for practice, what you can do, a couple of things. For example, you can try to define a XOR gate and see how will that XOR look like. XOR, remember, that is true if one of the values is true and false otherwise. If both are false, it is false. If both are true also, it is false. So you can see how to write that in terms of this. You can also try to, using the lambda expression, you can try to prove the De Morgan's laws, the complementation laws of Boolean algebra, and so on. So we'll just give you some good practice before you get into even more complicated lambda expressions. Here again, I have given some lambda expressions for practice. Okay. So let me stop and check if there are questions. Tanmay Balsa, please example. Tanmay, this question was quite some time earlier. Does
Sir,
it
it
still?
was answered.
This
I
has
have
been
asked.
answered. Right? Yeah. Okay. Right. Any other question? Anybody? Okay. So what we have done so far is we have shown certain simple example Boolean lambda expressions, and we have shown some ways to apply and compose, and then we have shown an abstraction to be able to build a Boolean algebra. Actually, things go well beyond that. For example, you can have a complete natural number system. In fact, you can have an integer number system also. It's a little bit more complicated based on based on the lambda expression. So all that you need to think of is given you have a successor function. So all numbers can actually be represented in terms of 0 and successor function. 0 is 0, start with that. And then if you apply successor once, you get 1. If you apply successor twice, you get 2. If you apply successor thrice, you get 3, and so on. So based on this, a number system was designed by Church. So wherein a number will be the number of successors of 0 that it is. So it is basically the number of times you apply a function f onto x. So to differentiate it from natural numbers, the numbers that we are familiar with, we write the Church numerals with a overscore. Okay. So the lambda expression is fx, lambda f dot lambda x. N is a natural number n applications of f on x. So apply like that. So what is the 0th number? Church numeral 0 is when you do not apply f on x. So n is 0, so no application. So it is lambda f, lambda x dot x. That is, considered that to be the 0 of the number system. I mean, we are breaking barriers here. I mean, you have to be mentally more flexible and open to conceive these kind of abstractions, because 0 and 1 are, I mean, since almost we have our senses, we have the notion of 0, 1, 2, 3. How many chocolates I have? I have 3 chocolates. So you don't think about that as anything other than counting on the fingers. But here we are saying, how does it matter? How does it matter? As long as I can have a lambda expression which represents a unique number, it is that number. And I would be able to perform operations based on that. So I've said that the representation of Church numeral n is the number of times you have applied a function f on a parameter x. So 0 application gives you, so this expression stands for Church numeral 0. Then you have 1 application of f, you get Church numeral 1. You have 2 applications of f, you get Church numeral 2, and so on. So this is my number system. So if I have that number system, all that I need is I need to be consistent with what my natural number system do, right? So in my natural number system, if I have 5, I have a successor 6. If I have 6, I have a successor 7. So I should be able to define an operator which, given a number, gives me the successor. and I define the successor in this charge numeral by this lambda expression. Lambda n, lambda f, lambda x, f, nf, x. The idea is simple, is if I have a charge numeral n of which I'm looking for the successor, then the function f is applied n times in that numeral onto x. That has been go back previous. That is the basic concept. So what do I need to do in successor? All that I need to do, I take that charge numeral which has n applications of f and apply f one more time onto it. Then it becomes n plus 1 applications and it represents the charge numeral n plus 1. So let's see, let's just do a longhand. If what is successor of 0? This is a successor function and this is my 0 applications of, so this is my charge numeral 0. Okay. So I have to apply this successor onto this lambda expression, so which means n is replaced by this. So there's only one instance, so that instance happens here. N goes out, this is what I'm left with. Okay. So naturally now you have a little bit of an issue because you can see that you have a bound variable f here and you have a parameter which is also f here, which is free. Okay. So you have to replace f by f, gets confusing. So similarly, you have to replace x by x. X is bound here and x is free here. So what you do a simple renaming. The bound variable, it does not matter if you change the name of the bound variable consistently. So you change f to g, you change x to y. Now you do not have the name clash, so you replace it here. G has no instance in terms of lambda y dot y. So if you replace, nothing happens. It becomes lambda y dot y. And then you have x. As you apply here, it becomes x. So you have lambda f, lambda x, fx. Now what is this expression? One application of f on x, which is charge numeral 1. Okay. So you can see that this successor lambda expression can very easily actually do this. You can try to prove this for n in general also. Gets a little bit longish, but so I have just done examples here and then I have shown you the derivation for n in general, but here is for 1. So if you take this successor of 1 charge numeral 1 here and replace it onto this, you do the same thing, you do the renaming, keep on applying, you will get fy will become fx and then you have f of x, which is 2 applications of function f on x, which is basically charge numeral 2. Okay. So this is for n, and this is kind of foundational because if you're aware of Peano's axioms, you'll know that all that you need actually to define the natural number system and operations is the successor function. In terms of general integer, you need successor and predecessor both. But for natural number, you just need successor. So addition of x and y is nothing but y successor of x or x successor of y. So you can just keep on add xy is nothing but doing successor of x y number of times. Similarly, multiplication can be defined in terms of addition. So if you have successor, you can actually build up the whole number system. So that is what I have shown here. We'll put up the slide and I would request you to go through how these different operations beyond successor, how add has been built up, then multiply. Once you have add, you can do multiply. Once you have multiply, you can do exponentiation. So how is these being built up? So that gives you a complete number system in terms of the natural numbers using just the lambda expression. So you can, I mean, this is my whole idea is not only just to tell you what are lambdas, but also to show you that it is powerful enough to define in a very formal mathematical manner the usual semantics that we have in terms of programming or in terms of our world. So we can keep on extending this, but the basic thing is what we deal with in programming is Boolean variables and expressions and integer arithmetic. Rest of it are all extensions which are approximated in terms of this. So naturally, the lambda expressions are being shown to be able to capture both of that. Of course, we will not do a natural number arithmetic using charged numerals because that is unnecessarily complicated. Rather, we will assume that those are available, add, multiply, and the numerals are available as predefined constant as we have done. But the idea here is to show that it is possible to do that whole integer arithmetic, represent that in terms of lambda expression. That is the power of the system. So then later on, I have just given some references for the predecessor function. It's a little bit more gets a little bit more complicated because without the predecessor, you cannot do a whole set of integers and you cannot do define subtraction. So the predecessor function and so on, and there are some practice problems. So I will stop here. The last few add, multiply, and all that I will request you to go through before you come to the class on next Monday, right? Next Monday, so that you have some confidence and go through this. The difficulty with lambda calculus is it is too easy. So when you read through something in lambda calculus in terms of abstraction or application, it seems too obvious. But when you close the pages, close your eyes and try to do that yourself, it gets tricky at times. So going through and practicing the problems that I've mentioned is quite important. Please try to do that. Let me stop here in the last couple of minutes. If there is any question at the end, let me take that. Any question from anybody in terms of the lambda calculus syntax? We still have a few fundamental thing to cover, primarily the recursion, which we will do in the class on Monday. But up to this point, this is a basic definition and basic power of lambda calculus that we have tried to discuss and show. So if there is any question, then I can answer. Otherwise, we'll take it off. Any question, anyone? There seems to be none. Okay, okay then. Thank you very much for attending. So we will upload both the module 1 and module 2 slides in Moodle today, and please go through that. In module 1 also, I would request that you go through the slides because there are certain points